Hello everyone, and welcome to your CMY 382 Experiment 1 Pre-Practical lecture. In this experiment, you'll be looking at activated carbon, sometimes also referred to as activated charcoal. And basically, if you just do a Google search of activated charcoal, you get an array of different products, including tablets, toothpastes, skin masks, and they all use activated charcoal to remove some sort of toxin or unappealing yellowness or acne or something that you don't want, essentially. And it removes it by a process called adsorption. Now, you might have thought the first time you looked at the experiment that there was a typing mistake throughout the experiment, but technically, so there's adsorption and there's absorption in chemistry. So let's start with absorption, AB. So in absorption, you usually have a molecule, atom, ion, or whatever, for like here as your X ion or a metal ion, or like I said, a molecule or atom, which is absorbed in or solvated in some sort of solvent molecule. So basically, if you want to think of it in a substance, it moves in between the layers of the substance. Whereas with adsorption, it's a surface phenomena. So your gas molecules or atoms or ions, once again, sit on the surface and get adsorbed to the surface of some sort of cluster of compounds, or like I say, a lump of activated charcoal here. So basically, it's just a nomenclature for distinguishing between when we are working with something that dissolves something else. Remember, we also get solid state dissolutions. Things can dissolve one another in the solid state, which is really quite cool, but that's a different topic. And then you get gas molecules. Well, so in this case, the gas molecules can get adsorbed to a surface. So anything that adsorbs to a surface, meaning that there's some sort of van der Waals interaction that brings it closer to the surface and makes it stick to the surface. Not really stick, but you get the idea. Just as you have hydrogen bonding here or some sort of dipole interactions or charge interactions, you can have the same thing here, except this is a surface phenomena. So it doesn't really, it just sits on the ring, if you want to put it like that. Now, in this experiment, you're going to specifically look at the adsorption abilities of activated carbon. That's why we've been focusing on carbon. I've been using the word. And you're going to see how well it adsorbs acetic acid from solution. Acetic acid also is a substance that can cause teeth yellowing. So, in other words, the charcoal toothpaste is a very good example here of how it works. So you're going to test how well carbon adsorbs acetic acid from solution. And the way you're going to test that is by setting up 7 Erlenmeyer flasks, each containing 1 gram of activated charcoal, the black lumps, and then having a different concentration of acetic acid. So in other words, it's a solution of acetic acid in water. So 100 milliliters of this solution, but different concentrations of 100 moles. So in other words, 100 moles of 0.5 molar, 100 moles of 0.4 molar, etc. And you'll also use a pipette to transfer all of this to your Erlenmeyer flasks. Remember, you'll also weigh by difference in terms of your activated carbon, but that will be explained better in the experimental video. Then, so for now, the blue dots indicate acetic acid molecules. So as you can see, higher concentrations has more of them, lower concentrations have less. All right. Thereafter, once you've prepared these 7 flasks, you're going to place them in a water bath for 1 hour at 25 degrees Celsius. The question I want to ask you is, why in a water bath? And hopefully you sort of have some sort of chemical intuition that tells you that it has to do that we want to keep certain parameters constant, and that perhaps at a different temperature, the adsorption isotherms, so there's the word, isotherm. What does isothermic mean? The adsorption isotherms will look differently at different temperatures. Why? Because you're going to have different rates of adsorption at different temperatures, because rates are temperature dependent. Okay. So now place your 7 Erlenmeyer flasks in the water bath at the temperature. The carbon is starting to adsorb your acetic acid molecules, and you've covered your Erlenmeyer flask with parafilm. This is not really how parafilm looks like. It looks more like a DC fix type of material, but for this purpose of illustration, these are parafilm. Okay, you might also place weights on them once you get to the lab. Okay, then while you're waiting for the hour to pass, you are going to have to standardize your acetic acid solutions, because we're not really quite sure what their exact concentration is, because they were made up by hand. So now, if you look, for example, your 0.5 molar concentration might actually be 0.47, because it was not analytically made up by an instrument. It was made by people, and we make mistakes, of course. Well, other people make mistakes, but anyway. Therefore, we need to standardize. So what standardize means is we're going to take a known standard concentration, or a known standard, meaning an NaOH solution, because remember acetic acid is an acid. So if you use a base, you can standardize it. You can neutralize. You have a neutralization reaction, which you monitor via titration and using phenolphthalein as your indicator. Depending on the concentration of the acetic acid, so 0.5 molar, 0.4 molar, etc., you need to choose either a 0.1 molar or 0.5 molar NaOH. Remember that acetic acid is a monoacidic, or what do you call it again? A monoprotic acid, that's the word. A monoprotic acid, so meaning it has one hydrogen. NaOH can accept one hydrogen, so OH can take one hydrogen. So in other words, 0.5 and 0.5 corresponds, 0.4, 0.5 still corresponds. But once you get to the 0.03, you might not want to use the 0.5 molar, because you're going to use literally 2 milliliters, and that's going to be too difficult to determine, to measure in your burette accurately. So choose your concentration of NaOH solution according to which you're relatively standardizing here. And then from there, you're going to determine the exact concentration. The reason you need the exact concentration is you need the exact initial number of moles of acetic acid, which could have potentially adsorbed onto 1 gram of carbon. There, so you've done that during the hour with your flask in the water bath. Now, like I said, the hour's passed, and your acetic acid molecules have adsorbed onto the carbon surfaces. And so in other words, our picture has changed a bit. Now we have, in certain cases, there's no acetic acid left in solution, and all have been adsorbed. So all the blue dots have become green dots. And at some concentration, this is not exact, this is not where it necessarily is going to happen. Please do not take this as your experimental section. At some stage, the concentration of the acetic acid is going to be too much to be adsorbed completely by the activated carbon. In other words, your acetic acid or your carbon is saturated. Just as a solution will become saturated, if you need to make a saturated sodium chloride solution, then there's a point where it's not going to dissolve anything anymore, right? So it's exactly the same principle here. At some point, there's going to be a maximum adsorption. So what is true of this diagram is you see here is, for example, 4 green dots, here's 5, there's a few more, and then they start to remain constant, and the number of acetic acid molecules in solution increases because we have a higher concentration. Okay, that's a very important part to note. So that make sure that you have the distinction between before and after the water bath. What is the picture looking like? So that you can do the physical chemistry from that point onwards. Okay. Now, of course, you want to determine what the concentration of the acetic acid is left after the adsorption has taken place. And the only way to do that is to standardize again. But first, a practical consideration that you need to have is you need to get the solution out. You want to be able to standardize it. And that's where the Bachner filter is going to come in. So you're going to filter your whole solution, so your whole mixture. You're going to mix it up well, and you're going to filter that through the Bachner. And first, you're going to just test 10 milliliters. You're going to discard that. The reason for this is in the first 10 milliliters, because there was an adsorption taking place, and you aren't going to be able to stop the equilibrium between adsorption and solvated molecules, because technically these are in equilibrium with one another. Your first 10 milliliters is going to be over-concentrated, and it's going to be an inaccurate concentration. So you discard the first 10 milliliters of the filtrate. Then you just chuck the rest, and that filtrate should be nice and homogeneously mixed. That's the reason why. You don't need to worry too much about that. Just make sure that you first filter about 10, so mix, filter about 10, discard that, and then you filter the rest of your mixture, so that you're left with the filtrate. And this filtrate should then just only contain the acetic acid molecules that are left after adsorption, and you'll have your adsorbed acetic molecules onto carbon will be left on top, because it's now in the solid state, because it's a surface phenomenon. Okay. And your final step is to determine what's the concentration of that acetic acid that's left in your flask. So take 25 milliliters of the filtrate, and you're going to titrate that with the appropriate NaOH, or sodium hydroxide solution. So again, if you're looking at the higher concentration acetic acids which you started with, a good starting point would be the 0.5 molar. Lower concentrations, a good starting point would be the 0.1 molars standard solution. And of course, you use phenolphthalein as your indicator once again. So then you determine what the concentration is in this 25 milliliters, which is going to give you the number of moles that are left. So you determine the number of moles you started with, and then number of moles in 25 milliliters. Remember, it's a quarter of what you started with. So if you started with 10 moles and there are 1 mole left in the 25 milliliters, technically in 100 milliliters there would have been 4 moles of acetic acid left. Make a note of that. If you're unsure, remember you can always ask questions during the lab to your demonstrator or myself. Okay, so what do we have? We started off with some initial concentration of acetic acid, and we had 1 gram of carbon in each of our Erlenmeyer flasks. So we had initial concentration, and from that we know we had 100 milliliters of each of those things in the flasks. In other words, we can calculate an initial number of moles. Then afterwards, we did a few standardizations to get the concentration of the solution after the adsorption. But we did that standardization on 25 moles. So we determined the number of moles left only in 25 moles, right? So if you want to compare these two mole quantities, in other words, the initial number of moles and the final number of moles, this value needs to be multiplied by 4, right? If you write it out logically, you will see it makes sense. Because here you start out with a number of moles in 100 milliliters, and here you only standardize for a number of moles in 25 milliliters. Didn't follow? Please go back to first year. Okay, then once you have those two quantities, in other words, the initial number of moles and the final number of moles, then you can calculate the number of moles acetic acid adsorbed per gram of carbon. Because remember, this difference then, NF or Ni minus NF, is then the number of moles adsorbed onto a gram of carbon, because in each of the Erlenmeyer flasks, we had 1 gram of carbon, right? Well, approximately 1 gram. So in other words, you can, if you had 1.0017 grams of carbon, then you just calculate, or you divide N by 1.0017, and you get exactly per gram of carbon. Okay. And then from there on, you are going to plot the different isotherms, which we will now look at. Okay, Then once you have N and C, you are able to tabulate N, C, log N, and log C. But then you also require some other parameters called N infinity and C naught. And to get those two parameters, you have to create a plot of N versus C. So notice N, so N is the difference in number of moles, so the number of moles of acetic acid adsorbed, and C is the concentration of the final acetic acid, so the acetic acid after adsorption, not the initial concentration of acetic acid, the final concentration of acetic acid. So please don't plot here the 0.03, 0.5. This is the one that you determine the second standardization concentrations. Okay, and a plot of that should give you a curve that looks something like that, which levels off. And you should ask yourself, why does it level off? Well, essentially, the reason it makes sense it should level off because there should at some stage be a maximum adsorption. So a maximum number of moles at which the 1 gram of carbon is no longer able to adsorb more, even though there is more acetic acid available for it to adsorb, or more acetic acid can adsorb. It's not possible. The capacity has been reached. The surface area is full. So all surface area has been occupied. And that's why it's called the N infinity. So in other words, the infinite number of moles, if you want to put it like that. So the maximum number of moles that can adsorb. And that corresponds to some sort of maximum concentration. And you can read that off from this plot. Your curve might not look perfectly as this would. So you essentially just do your best to get these two values, wherever they may be. Okay, and you take them as is, and you work with them further on in the next part of your report. All right. Finally, after you have all the parameters, the only thing that is left is to plot the 3 different isotherms. And you can plot the 3 different isotherms. It's quite explained nicely in the practical manual, exactly what you need to plot against what. And from that, you will see they should give you straight lines. And of course, from there on, you can see from the lines of best fits and of course the correlations exactly which isotherm fits the data the best. In other words, which isotherm is the most appropriate. You should also have a theoretical reason why that isotherm is the most appropriate from the information provided in the practical guide. So then finally, I just want to give you a hint for discussion question number 2. The question says at high KBET values and at low concentrations, the BET equation reduces to the Langmuir equation. You need to show this. So let's look at the equation. So there's a bunch of things on the left and a bunch of things on the right. So there's a C, there's a C, there's a C, there's KBT, KBET, KBET. And now a very important point is we're only concerned in parts which are called linear mathematical operations. So meaning plus and minus. You can't really say anything about division or multiplication. So where's the first? So let's first look at if C is very small. That is what low concentrations means. C is very small. So the only place where there's a linear operation is there. C naught minus C. So let's say you have something very big. C naught is 1,000. And you have something very small, 0.1. You say 1,000 minus 0.1. What's the answer? 999.9, right? Which is pretty much 1,000. In other words, C naught minus C is approximately C naught. Then again, we look for our next linear operation. So that's a division. We can't really say anything there. That's a multiplication. There's another division. There's a multiplication. But here is another linear operation. And now KBET is very large. So in other words, again, we have the same idea as we had here with 1,000 minus 0.1. So it gives us 999.9, which is very close to 1,000. In other words, this reduces also to KBET. So that is what it asks you to do. So now substitute that to C naught, substitute that with KBET, and then you'll see certain interesting things to happen. I mean, that KBET is going to cancel there and there. you have a C over N C naught, and you have here C over C naught, so maybe that's going to cancel, and then you need to rewrite it a bit, and you'll find the Langmuir equation. Okay, well, that's all for our practical lecture, and I will see you in the lab. Good luck.